Hello. I can see that nobody is here yet, but let's go ahead and get started. Okay, I've got a selection of different problems that I have chopped up from the quizzes that we took over the most recent couple of days. So what I'm going to do is, until somebody gives me a question to work, I'm going to just go ahead and work those. Okay, so go ahead and just type anything you want to me. I'll respond as quickly as I can, and if the questions are good, I'll keep going. I hope to be in and out in about half an hour to an hour. So let's see what we've got. Okay, so Ellen's car accelerates uniformly at a rate of 2.6 meters per second squared. How long does it take her car to accelerate from a speed of 88.5 kilometers per hour to a speed of 96.5 kilometers per hour? Okay, so now what I normally like to do is start off with what I call my 4 steps. It's a version of something every teacher has, but every teacher has these, so I'm just going to use mine. So first, write what you know. Step 2, write what you're looking for. Pick your equation. And then last, plug and chug. Just plug in the numbers and get going. Okay, so let's take a look at this problem one more time and apply our 4 steps. Ellen's car accelerates uniformly at a rate of 2.6 meters per second squared. Okay, so right off the bat, I can tell that is an acceleration. First, it says so, but also it's in units of meters per second squared. That's always going to be an acceleration. How long does it take her car to accelerate from a speed? So we have our initial velocity, 88.5 k per hour, to a speed. So we have a second speed of 96.5 k per hour. Okay. Now, what you should notice right away is that our acceleration is in units of meters per second squared, and our velocities are in units of kilometers per hour. So what we're going to have to do is a little bit of dimensional analysis, or just converting these meters per second into kilometers per hour squared. Okay, we just need our units to match up. Now we could convert these kilometers per hour into meters per second, or we could convert these meters per second squared into kilometers per hour squared. I'm going to go ahead and convert my acceleration into k per hour squared, because then I only have to do this once, whereas I'd have to do this twice. Okay, so let's take a look at our acceleration. Our acceleration is in meters per second squared. Now, if you're in my class, we've gone through this a little bit, but let's go ahead and do it again. So I have a fraction here, meters over seconds squared. Okay. Now, in order to get rid of this meters and replace it with kilometers, what I need is a meter in the bottom of a fraction. At the top of the fraction, I'll put k's, because that's what I want to replace it with. Now, for every 1 kilometer, there are 1,000 meters. Okay. Now, 1 kilometer equals 1,000 meters. So what I've just multiplied by right here is just 1. 1k over 1m is just 1. So that hasn't changed the value of this number. It's just changed the form in which it's in. So those 2 meters cancel out. Next, I got to get rid of these seconds and replace them with hours. Now, the second is in the denominator down here, so I need it to be in the numerator over here. And I'm going to replace it with hours. And because hour is bigger, I write 1 hour, and for every 1 hour, there are 3,600 seconds. Okay, now here's the part that might get a little tricky if you're not familiar with this process. This 1 second right here cancels out 1 of those seconds, but it's meters per second squared, so we actually have to do the seconds and hours conversion over again. We have to do it 2 times. So we have kilometers per hour per hour. So now if I take my calculator and do 2.6 divided by 1,000 times 3,600 times 3,600, I end up with an acceleration of 33,696 kilometers per hour squared. Now, that seems like a really huge number, and part of the reason why some teachers do this and why I do this is because that number will look confusing. And what I want you to do is to know your math well enough that even if the number looks a little confusing, you go back and check your math and know that it works out right. Okay, so now what are we looking for back here in our problem statement? It says, how long does it take her car to accelerate? So that's what we're looking for. We're looking for a delta t, a change in time. Okay. Hey, everybody who's out there, just type in a hi or something so I know that you're there and that you can hear me. Okay. Thank you. But so we're looking for time, right? Now, we're at step 3 here, and to pick our equation. Okay. Now, the equation that most fits what we're looking for here is going to be our acceleration definition of acceleration equals a change in time over a change, or a change in velocity over a change in time. Okay. Now, we weren't given a change in velocity directly, but so what we have to do is actually calculate our change in velocity. Now, another way to write change in velocity is v2 minus v1, okay? And we have those. 96.5 k per hour minus 88.5 k per hour, okay? And that just equals 8.0 k per hour, okay? Seriously, type in and say hi if you can hear me, because I'm starting to worry that nobody can hear what I'm saying. Anyway, so we have 8.0 k per hour, and we can replace our delta v here. But we're actually solving for this delta t down here, right? So I need to move this delta t out, okay? Now, if you're in my class, we've gone over this a little bit, but there are 3 different ways to organize this exact equation. They're all exactly the same, but they are organized a little differently. Okay, all 3 of these equations are exactly the same. Okay, A equals a change in velocity over a change in time. T equals a change in velocity over acceleration, or a change in velocity equals acceleration multiplied by our change in time. Okay, all those equal out the exact same way, but they just look a little different. So the one I'm looking for is the one that will give us time. So that's going to be this guy right here. That's the one I'm looking for. So I'm going to go ahead and write that over here. Delta t equals our change in time over our acceleration. So we have our change in velocity. Ah, dang, I keep saying that wrong, don't I? Oh, well. Our change in velocity, we already calculated it over here, is 8.0 k per hour. And our acceleration that we calculated up there is 33,696 k per hour squared. Now this k cancels out that k. One of these hours cancels out that hours, and what we're left with is what we're left with is 2.37 times 10 to the negative 4 hours. Okay. Now, again, that sounds a little ridiculous, and I'll admit it is a little ridiculous. Most of these problems are made up by us sort of on the fly a little bit, and as long as they don't give us like divide by zeros and stuff like that, it's fine. So here is our answer to the problem we just worked. Ellen's car accelerates uniformly at a rate of 2.60 meters per second squared. How long does it take her car to accelerate from a speed of 88.5 km per h to a speed of 96.5 km per h? And that's our answer right there, 2.37 times 10 to the negative 4th hours. And if we were to convert this into seconds, it actually ends up just a little less than 1 second. But, you know, that wasn't asked for in the problem, so we're not going to go ahead and do that. All right, now I'm going to go ahead and until somebody suggests something else, I'm just going to keep working problems out of our last quiz, okay? Okay, so let's take a look at this little guy right here. We have a velocity versus time graph. Okay, I'm going to draw this again, but anybody in my class should anybody in my L class should recognize this from the quiz. Okay, so let's go ahead and draw this out. Okay, so now this is a VVT graph, velocity versus time graph. We have 2, 4, 6, 8, 10. And we have 5, 10, 15, 20, 25, 30. Okay, good. It starts at 10, goes up to 30. There we go. Okay. Easy peasy. Now, one of my favorite things to do to help me understand what I'm looking for is to draw a picture. I have been doing physics for 7,000 years, and frankly, I'm going after my master's in physics. So I have a mountain of experience doing these. So it's much more easy for me to visualize in my head what a problem is going to look like. You guys, as physics K and L, and even maybe a little AP students out there, are going to be new at this, which means that you haven't necessarily developed the mind's eye to see how these things work. So we're going to go ahead and examine this particular graph in detail. Okay, so along my x-axis here I have my time, and along my y-axis here I have velocity in meters per second. Okay, so let's start off by examining this overall thing. Okay, so velocity versus time graph, and let's see what it's actually telling us. Now, this line is straight, not curved, which means that it has a uniform rate of change. And because it's a line, we have another word for that rate of change. That rate of change of our velocity is just our slope. You probably recognize this from the y equals mx plus b formula that you're familiar with from algebra, but our m is just going to be our delta y, delta x, probably also have heard it called rise over run. Now, if we replace our delta y and delta x with what we have on our x and y axis, we see that our delta y is in fact our delta v, and our time is on our x-axis, so our change in x is actually our delta time. Now, from our last problem, you probably recognize delta v over delta t as acceleration. Okay, so the point there, let's go ahead and wall off my steps and start writing down things that we know over here. On a VVT graph, the slope m equals acceleration. Okay, so if you have a velocity versus time graph, then its slope is always equal to the acceleration, whether or not it's straight or curved. But now that since we can see that it's straight, we know that the acceleration is the same here as it is here. Okay, next. What is this graph telling us by starting here at 10 meters per second instead of at 0 or something like that? Again, looking at our y equals mx plus b formula, you probably recognize this 10 over here as our y-intercept. Okay, now our y-intercept in any graph at all shows us the initial value at x equals 0. Now x is time on this graph, so at time equals 0, we have a velocity of 10 meters per second. So on a VVT, on a velocity versus time graph, our y-intercept is our initial velocity, our v0. Okay, just in case anybody's quiz asks that question. Okay, And because this is a VVT, anybody out there who knows any calculus, the VVT, the velocity versus time graph, is going to be the derivative of the position graph. And in order to go backwards, we need to take the integral of the graph. And the simple way to take the integral of the graph, especially when it's a nice square shape like we've got right here, is to calculate the area under this curve. Okay, so in a velocity versus time graph, our change in position is equal to area under curve. Okay, area under the curve. So let's go ahead and calculate that after we finish up our y equals mx plus b. Okay, so what we have here is we have an equation for calculating our acceleration, our slope of the line. We've already written down our y-intercept. So our change in velocity is going to be v2 minus v1 over our change in time, or t2 minus t1. Now v2, our final velocity, is way up here at 30. Our initial velocity is way down here at 10, so 30 minus 10. Our final time is over here at 10, and our initial time is over here at 0. So we have 20 divided by 10, or 2 meters per second squared. Okay, so our equation of the line shown here is our velocity in meters per second is going to be equal to 2 meters per second squared multiplied by time plus 10 meters per second. That is our equation of the line. Okay. Now we can do two things. If you know calculus, which would be a little surprising, you can just take the integral of this equation and calculate its value between 0 and 10, and you would get the total distance traveled. But we're going to do it the easy way. It's actually a little quicker, and that's what we're going to do instead. So you see that I've drawn two shapes on my graph here. One's a rectangle and one's a triangle. So what we're going to do is we're going to calculate our change in x by figuring out the area of this rectangle plus the area of the triangle. So the area of a rectangle is just the length times the width, and the area of this triangle is 1/2 the base times the height, right? Okay, good. So our length of our rectangle is 10, and our width is 10, plus 1/2. Our base of our triangle is this 10 right here. And then the height of our triangle is the distance between 10 and 30, or 20. Okay? So that ends up being 100 plus 10 times 20 is 200. Half of that is 100, or a total change in position of 200 meters. Okay? That's our total right there. But before we move on, I want to show some of the foundational math here. Okay, so it seems, and this is how I wanted it to seem, that it's very, very easy to just calculate this area and move on from there. Okay, but if you guys in my class recognize this equation from my equation corner, and probably from the discussion in any of your other classes, I don't know who's watching, but let's take a look. So we already said that this 10 over here was our initial velocity. We called that our length over here. So let's go ahead and write that in as V0. Now our width right here was our change in time. So let's write that in as delta t. Now 1/2 is 1/2. But our base, now let's talk about this one right here. Okay, so our distance between 30 and 20, our height, is our change in our velocity from our initial to our final. And another way to write that is delta v. And then, of course, our base is change in time again, so delta t. You guys probably recognize this equation. Or if you don't, it's probably because it's usually written in a different form. So let me go ahead and show what that different form is. So we already know, we've defined it as our acceleration is delta v over t. Now if I substitute a into this equation where this delta v is, I end up with what you're probably more familiar with, v0 multiplied by delta time equals 1/2 a delta t squared. That's probably what you're a little more familiar looking at. But both of these versions of the equation are exactly the same. They behave exactly the same. The only difference would be you could use this one when you know the acceleration, when you know it. And you can use this one when you know two velocities, or if you're looking for a velocity but don't know the acceleration. Okay, so they're organized differently, but they still work. So let's move on to the next one. And again, I'll just keep doing problems out of my quiz until somebody suggests something else. Okay. What do we got? All right. A quick one. All right. Is it all still in focus? If you can't read the thing, let me know. All right. A truck has an initial velocity. All right. Writing what we know. Initial velocity of 1.3 meters per second. And accelerates 0.5 meters per second squared for 8 seconds. Delta t equals 8 seconds. What is the final velocity of the truck? The final. We don't know. Okay, so we've already done step 1, write what we know. Step 2, write what we're looking for. And now it's time to step 3, pick our equation. Okay, what is the final velocity of the truck? Now, again, I'm going to go ahead and apply the general form of this equation. But since I'm looking for a velocity at the end there, what I'm going to do is instead use the slightly different but exactly the same organization of that. Delta v equals acceleration multiplied by delta t. Okay, and like we talked about a couple times already, delta v can also be written as vf minus v initial. Okay, and now if we combine all that together, substitute everything in, we have vf minus v initial equals acceleration multiplied by delta time. Now, in order to be able to use any particular equation, we can only have at most one unknown. All right, so if you have more than one unknown, you can't use the equation. So let's go ahead and check. Now, we don't know delta, or we don't know vf yet, but we do know initial velocity, we know the rate of acceleration, and we know our change in time. So we only have the one unknown. All right, that leaves us able to figure out this equation. So step 4, plug and chug. vf minus 1.3 meters per second equals 0.5 meters per second squared multiplied by 8 seconds. Okay, so this seconds cancels out that, and we're left with a meters per second. So again, we can keep track of our units and use those to make sure we're on the right path. Okay, now let's go ahead and do that math. 8 times 0.5 is 4, so vf minus 1.3 meters per second equals 4.0 meters per second. Now if I add 1.3 to both sides, what we end up with is vf equals 5.3 meters per second. Okay, but since I like to do these kinds of problems, what I'm going to do now is add in one piece that we hadn't originally talked about. I want to know how fast or how far the truck goes in those 8 seconds from the time it starts off at 1.3 meters per second and accelerates up to 5.3 meters per second. Okay. Now, we didn't actually need to calculate this part in order to find that just yet, because if you remember from a second ago, our equation for delta x is v naught delta t plus 1/2 a t squared. Now, again, let's check and see if we can use this equation. We do know our initial velocity, we know our time, we know our acceleration, we know our time. The only thing we don't know is this x right here. So let's go ahead and plug and chug again. 1.3 times 8 seconds plus 1/2 times 1/2 times 8 seconds squared. Okay, So 1.3 times 8 is 10.4. 1/2 times 1/2 is a quarter. 8 squared is 64. 1/4 of 64 is 16. So our total change in position over this 8 seconds right here is 26.4 meters. Okay. And actually, that was going to be the next question, but I went ahead and did it anyway. So there we go. That's relatively easy, straightforward. Okay. So, any questions right now? Let's make sure that the chat works. Hi. Nope. Nobody else? Okay, fine. Moving on. You guys can screenshot these. This will be up as a public video as soon as I'm done with this, but it'll be fun. I hope this is all working out for everybody. Okay. Let's do this one. This one's one of my favorites because of how simple and confusing it is at the same time. All right. A ball is thrown vertically upward with a velocity of 25 meters per second. That is our initial velocity, 25 meters per second. How high does it rise? So delta x. Little tip, if you're working on a dry erase board, make sure that your ink dries before you try to erase it, or it'll smudge. We're looking for delta x. How long does it take to reach its highest point? Delta t. How long does it take to hit the ground after it reaches its highest point? So let's say delta t2. And what velocity is it when it returns from whence it started? So let's say vf2. Okay. So now, especially for problems like this that have an up and a down portion, it's nice to draw out a picture. So I'm going to draw out a picture. There's my ball. It's traveling upwards. It starts off at 25 meters per second. Now, if you've ever thrown anything in the air, you know that you'll throw it up in the air and it'll start off quite fast and then it will slow until it hits some maximum height where it actually stops just for a second, just for that fast, and begins to turn around and come back. So we actually know our final velocity and our initial velocity for this first half. And that's where we're going to figure out how high the ball goes up, is just on that first half. Now, one piece that we're missing that would help us calculate all this is our acceleration, right? Okay, so here's the problem. We actually know our acceleration. Unless it says something different, we can reasonably assume that everything that we do in physics happens on Earth. Okay, so we can reasonably assume that we are on Earth. And on Earth, our acceleration due to gravity is negative 9.8 meters per second squared. And now that negative just means that the acceleration is towards the center of the Earth. No matter what side of the oblate spheroid that we're standing on, the acceleration is towards the center of the Earth. And we have defined that as down generally. Okay. Now, if we called up negative and down positive, then the sign would change, but that doesn't matter. As long as you're consistent throughout your math, you'll be fine. Okay. So now we know all these things. And us tricky physics teachers, we will say things like starts from rest. That means zero velocity, or dropped out of a tree, which means zero velocity, or red light, which again means zero velocity. And usually, well, it can only really work with falling problems. We won't give you the acceleration. So if we don't give you the acceleration and the problem involves falling, the acceleration is probably negative 9.8 meters per second squared. I didn't say always because it's not always true, but it's usually true. Okay, so let's go ahead and solve this problem. So we're given a initial velocity. We know, we deduced our final velocity and our acceleration. So let's go ahead and start off. I actually want to start off calculating this time right here because it's the easiest. So delta t is equal to our change in velocity over our acceleration. Okay, v2 minus v1 is delta t, or delta v, and acceleration is acceleration. Okay, so our final velocity, like we said, is 0. So 0 minus our starting velocity of 25 divided by negative 9.8. Now, we can see here why it's so important to keep our directions straight. Because of the way this is, our change in velocity is actually negative, divided by a negative acceleration. And that will guarantee that our time that we are given, that we calculate, is positive. Because there is no such thing as negative time. Okay, it's one of the few things that we all know about our universe is that time only moves in one direction. Okay, so we have calculated our time using our acceleration equation. Okay, so we have a time of 2.55 seconds. And now, because we know that, we can use our long form equation of our delta x over here. So delta x equals initial velocity multiplied by time plus 1/2 acceleration time squared. Okay. So v0 multiplied by delta t. So that's 25 times 2.55 plus 1/2 negative 9.8, 2.55 squared. Okay. Now let's go ahead and punch that into our calculator. 25 times 2.55, 63.75 plus times 2.55 squared, or negative 31.86225 plus. So we end up with 31.8775 meters into the air. Okay, and actually we could solve this in a different way, but I'll talk about it. I'll talk about it in a second. Make sure that we use that other equation. Okay, so we solve for how long it takes to get to the top. We solve for the height of the object as it gets to the top. Now we need to figure out how long does it take to hit the ground after it falls, as it falls from its highest point, and what velocity is it when it hits the ground. Okay, now here's the part that aggravated my students before. Our delta t2 is equal to the amount of time it takes to get to the top. So because gravity accelerates everything uniformly, it will slow things down as it heads up, and then it will speed them up as it comes down. And no matter how high up, it'll take the same amount of time to go up and down. A throw like this will. And when it hits the ground, it'll actually, our VF2 will be equal to what our initial velocity was. So our VF2 is just equal to 25 meters per second. Now, if you don't believe me, let's go ahead and figure that out. Okay, so we know since the object goes all the way to the top of this 31.88775 meters, we know it has to fall from that height too. And actually, this is a good way to use my other equation. You may or may not have seen this equation. I don't use it all that much, but let's go ahead and use it anyway. Now, I'm going to go ahead and use this equation because it excludes time. We don't need it. And I'm more interested in figuring out what it is minus this time, just in case for some reason this time is wrong. Okay. We know that at the very start of the fall, that this velocity has to be 0. It's starting from the point where it turns around. So the ball goes up and goes up and slows and slows and slows and then stops, then speeds up and speeds up and speeds up. That's how that works. Okay, so let's go ahead and use this equation. We're looking for this final velocity. We know that our VI in this case is 0. We know our acceleration is negative 9.8, and we know the distance is the same as this guy over here, so 31.89. Okay, so let's plug all this in. This term disappears because it's 0, so 2 times negative 9.8. And since it's falling, this is going to be negative 3.18875, and so on. And we end up with VF squared equals 625 meters squared per second squared. We need to take the square root of both sides, or boom, VF equals 25 meters per second. Okay? Boom, there we go. All right, so we've been in for 36 minutes. I have just been doing problems all by myself with no input, so I'm going to go ahead and do one more, and then we'll be done unless somebody suggests something else. Okay? So feel free to take screenshots or any of this stuff. And because of the way YouTube does their thing, this will become a public video as soon as I'm done. Okay. So this one, well, which one was the most complicated one? I don't know. Actually, let's go ahead and do this one. And then I might do that last one. I might do that other one last. Okay. So a truck covers 60 meters. That's our delta x. 60 meters. That is a delta x. Let's see if it's our only one. In 10.5 seconds. That's a time. While smoothly accelerating to a final velocity of 5.5 meters per second. What was the original velocity? V0? We don't know. What's the acceleration? A. We don't know. All right. So let's go ahead and start working that out. Okay. Now I am having a little bit of a brain fart. Okay. So. Oh, okay. Now I remember. All right. So delta x. We're going to go ahead and start with the version that I showed y'all a little while ago. All right, delta x equals v naught delta t plus 1/2 delta v delta t. Now, this is an instantly attractive candidate because we know delta x and delta t. But let's see if we can work this out since we don't know v0 yet, which means we don't know delta v. But, as I've mentioned a couple times during this session, delta v is equal to v2 minus v1. Now, if we substitute this guy into there, we can rewrite this equation as v0 multiplied by delta t plus 1/2 vf minus v0 multiplied by delta t. Now, let's see whether or not we know enough. We know delta x because it's given to us. We don't know v0 because it's not given to us, so we don't know that one. We know delta t because it's given to us. We know final velocity because it's given to us. We don't know original velocity because it's not given to us, and we know our time, which means that we only need one thing. So we only have one unknown in this equation, which means that we can use this equation. So there it went. Let's go ahead and do step 4, plug and chug. So 60 equals v naught, we don't know what that is, multiplied by 10.5 plus 1/2 5.5 minus whatever v0 is, multiplied by 10.5. Okay. Now, if you remember your algebra, you should notice that there's a 10.5 that we can factor out here. So let's go ahead and divide both sides by 10.5. And 60 divided by 10.5 is 5.71 equals V0 plus 1/2 5.5 minus V0. Okay. Now all we have to do is multiply through here and then combine like terms. So 5.71, this V0 is going to be combined with this negative half of V0, and V0 minus a half of V0 is just 1/2 V0. Plus 1/2 of 5.5, which is 2.75, or plus 2.75. See, positive, positive. Now, subtract both sides, 2.75. We end up with 2.96 equals 1/2 of V0. Okay. Multiply both sides by the reciprocal, and we end up with V0 equals 5.92 meters per second. Okay, that's our initial velocity. Now, if we apply our acceleration equation, delta v over delta t, and our delta v definition of v2 minus v1, we can see that by plugging it in, we have 5.5 minus 5.92 divided by 10.5 seconds, which actually ends up being, let's see, I might have done that one wrong. Yep, I just messed that up a little bit. There we go. And if you notice, this one's smaller than that one, so this is a negative. Okay, so there we go. That one was pretty quick. It seems a little tricky because you've got to do some substitution to get there, but other than that, it's relatively straightforward. So let's go ahead and do one more before I sign off. Okay. Okay. A truck on a straight road starts from rest and accelerates at acceleration 4.0 meters per second squared until it reaches a velocity of 40 meters per second. The truck travels then for 85 seconds at a constant velocity until the brakes are applied, stopping the truck in uniform manner in an additional 10 seconds. Interesting thing, like I said before, we just hit in a piece of information, stopping the truck. So that means over this piece of time that our final velocity is 0. Okay. How long is the truck in motion? So let's say delta t total. And what is the total displacement of the truck? Delta x total. All right. Now this is going to be a perfect candidate for drawing a picture. Okay. So we have here, we're going to draw a velocity versus time graph with v on one side and t on the other. Okay. So it starts from rest. So our initial velocity over here is 0. Okay. Starts from rest and shoots up to a velocity of 40 meters per second with an acceleration of 4.0 meters per second. Now I want to see what time goes in there before I draw my picture. So let's go ahead and use our time equation. Time is equal to delta v over a. Our change in velocity is from 0 to 40, or 40 divided by 4 meters per second, our acceleration. So our time is 10 seconds. So over 10 seconds, does that look okay? 10 seconds. It goes from 0 to, let's say, up there, 40. Uniform acceleration, boom, there we go. Now we know that it then holds that speed for 85 more seconds. So from 10 to 95, right? Because there's 85 seconds in between there. And then 10 more seconds until it stops. So that would be over here to 105 seconds and down to 0. Okay, now if you pay close attention, what we've just done is actually calculate this total time. We had 10 seconds here, 85 more seconds, and then 10 more seconds. So our total delta t is 105 seconds. There we go. Boom. Okay. Now we're going to do what I did in my very first problem and calculate the area under this curve in order to get our total displacement. Now I'm going to go ahead and do it that way and then show you how it is actually the hard way, but don't be afraid. So the total x is going to be the area of this triangle, or 1/2 base times height, plus the length and the width of this rectangle, and then the area of this triangle, or another 1/2 base times height. So the base of this original rectangle or triangle over here is 10. The height of that triangle, as you can see, is 40. Plus the length of this triangle here is 85 times the height of that that rectangle, which is again 40. Plus again 1/2 10 times 40. Okay. Now if we punch all that in, we have 10 times 40, which is 400. So half of that is 200. 85 times 40 is 3,400. I happen to know that, but let me make sure that I'm right. Yeah. Plus another 10 times 40, or 400 divided by 2, 200. So total 3,800 meters. That's our delta x. Okay. Now that one's pretty quick. And again, I want to show how we actually did all the calculus throughout this whole thing, even though we just, imagined it a little easier than it is. So in this first part right here, if we look at the original equation, we can see that our initial velocity is 0. So this term drops out. 1/2 multiplied by 4, which is our acceleration, times our time, which is 10 squared. So 1/2 times 4 is 2. 10 squared is 100. So 2 times 100 is 200. See what we did there? Next, delta x2. Again, if we look at this, plus 1/2 acceleration times squared. We see that our acceleration over this period, because it's a 0 slope in this section right here, in this B section, we see that acceleration is 0, so this term drops out. And we end up with our initial velocity for that period, which is 40, multiplied by our time for that period, which is 85 seconds, or 3,400 meters. See what we did there? And then last, delta x3, v0, delta t plus 1/2 delta v delta t. Again, remember, these two are the exact same. They're just slightly different forms. So don't get all trippy on me. Our initial velocity for that period is 40, multiplied by our time, which is 10, plus 1/2. Our change in velocity was from 40 down to 0, so negative 40, multiplied by our change in time, again, so 10. 40 times 10 is 400, plus 1/2 times negative 400, or minus 400 minus 200, or 200. Again, see what we did there? Okay. So I understand that at least some of you have a test tomorrow, so I want to wish everybody good luck on that. And I want to say just how nifty it's been to see upwards of 8 whole viewers in some spots. So I want you guys to, I hope this worked out. I hope this was a lot of fun for you guys, or at least very informative. And I will see you in class.